Hey guys, want to preface this video with the following. Students, if you are in my A-Day classes, this video does not match the notes you had because I did a major rewrite from A-Day to B-Day. So sorry. You can still watch this. It's still the same content, but it won't match the notes that you had. If you were absent on A-Day, that was January 13th, then the notes that you picked up as an absent student do actually match this video, but sorry, A-Day students who were there live, this video is different than the notes you had. Same content, you can still watch it, a little bit different than what you had. Anyways, all right, here we go.
Those graphs that repeat their shapes over and over again, three of the most important ones we're going to talk about in this class are functions called sine, cosine, and tangent. Now, we're not going to graph them just yet, but we need to understand what sine, cosine, and tangent are telling us. In geometry class, you would have learned sine, cosine, and tangent in a triangle. Okay, you would have done SOHCAHTOA, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Do those words sound familiar? Great, it is still the same stuff, except now we're not putting this in a right triangle. We're going to be using sine, cosine, and tangent on a coordinate plane. It's the same things you learned when it's a triangle, because it honestly makes a triangle, but we're not just going to have a cute little right triangle to look at the sine, cosine, and tangent. We're going to put this on a coordinate grid. Being that we put them on coordinate grids, we need to approach these angles that we're using in a different way than you probably have before. For my class, usually angles are going to be represented by a Greek letter. The most common Greek letter we use is theta. This is why I was super annoying last semester about crossing your zeros. A zero with a cross through it is actually the Greek letter theta, a horizontal line. That means an angle. It's a variable that represents angles. We might also use alpha, beta, and omega, but this is the normal one that we use most often. We approach angles in a generalized method that allows us to view them through a periodic lens. To do this, we must make first some definitions very clear. When I'm talking about an angle, I'm talking about an angle in standard position. You're going to see that phrase over and over again. What I mean is that in the coordinate plane, an angle is in standard position when its vertex is at the origin, and one ray of the angle lies on the positive x-axis. So we have, that is a tiny highlighter, let me make that a little bit bigger. We have this angle right here, this side of the angle, sorry, the ray that is along the positive x-axis. That is always the initial side for angles that I'm talking about on a coordinate grid. The second definition we have is called the terminal ray. The terminal ray of an angle is the second ray of that angle. So as we open up where we're ending that angle, that is your terminal ray. So you have your initial side, you have your terminal ray, the vertex is at the origin. This angular direction that we are turning is your angle theta, which means theta can be an acute angle. It can be an obtuse angle, it could be a right angle, it could be a straight angle, or it could be an angle larger than 180 degrees. So we are looking basically in a circle around our coordinate grid for how many angles we are moving, how big our angle is we're moving around this coordinate plane. Good morning. Oh, yay. All right, so what are the definitions of sine, cosine, and tangent in this context? Thank you for asking. Sine, cosine, and tangent are values around this circle. So in an angle, given an angle in standard position, so starting at the positive x-axis, moving counterclockwise around, there is a point P. We're going to highlight point P in orange. Point P where the terminal ray intersects the circle. So if we look here, we have our initial side as the positive x-axis. We have theta moving our terminal side to be right here. Where that terminal side meets this circle centered at the origin is called point P. Obviously, since this is a coordinate point, point P has a coordinate x comma y, an x distance, horizontal distance, and a y. Now, sine is the ratio of the vertical displacement of P from the x-axis to the distance between the origin and point P. If we look at the vertical displacement starting at the x-axis and arriving at point P, what value is that? What is this diagram labeled that distance? It's labeled as y because that is the height that point P arrives at. So it is the y coordinate of that point P. But sine is the ratio of that vertical displacement to the distance between the origin and point P, which means that is our radius. In triangle language, compared to theta, that is still the opposite over the hypotenuse. But for us, since we're not looking at a acute right triangle, we're looking at a coordinate plane, that is the vertical displacement, y, and the radius, which acts like your hypotenuse. So sine is y over r, the vertical displacement divided by the radius, or y over r. Cosine is defined to be the horizontal displacement of P from the y-axis and the distance between the origin and point P. If I look at the horizontal displacement of P, I'm looking for how far side to side from the y-axis it is. That is labeled as y. I'm sorry, it is labeled as x, which means cosine is the ratio of x divided by r. In triangle language, and I would have to move that blue line down here to make it a triangle, that is still your adjacent and your hypotenuse. So we're still using the definitions from your geometry class previously, we're just putting it on a coordinate plane. That is your x value of P and your radius of your circle. Tangent is defined to be the slope of the terminal ray. Think back to Algebra 1, what's the formula for slope? Or like, what did we use to find slope in Algebra 1? Rise over run. Yeah. If I start here and I go from this beginning point to this point P, how much did I rise? How much did I run? So tangent is y divided by x. It is the ratio of the vertical displacement to the horizontal displacement. In triangle language, it is the opposite, y, divided by the adjacent, x. We're still using the same definitions. Additionally, because you can keep, change, flip these fractions, tangent is also defined to be sine over cosine, and that's going to come into play a lot for us later on in this unit when we start doing trig identities, that tangent is sine over cosine. Already right here, we have 3 new definitions that can possibly definitely be on your formula quiz for next class. Here's a little look behind the curtain though. It is my biggest pet peeve if I hear sin, cos, and tan. That is sine, cosine, and tangent. We're going to say it correctly. It is not sin, cos, and tan. Sine, cosine, and tangent. Okay? You owe me a quick buck if I hear you say sin, cos, and tan. Questions, comments, concerns? Those are the definitions of our 3 trig functions on a coordinate plane. Sine is y over r, cosine is x over r, tangent is y over x. Same SOHCAHTOA as you did in geometry class. So let's see what a question might look like here. It says the figure shows a circle with radius 5. That's important. Let's highlight that for a second. What is our radius length? 5. If we didn't have this printed on the little blurb, how else could I know from this picture that my radius is 5? Yeah, look at the point right here. If that's 5, 0, that means my radius is 5. So whether or not they tell you, they're going to tell you somehow, either in the picture or in the words, what the radius is. Okay, we keep reading. Figure shows a circle with radius 5, check, centered at the origin with an angle of measure theta in standard position. Check out theta. We go from here all the way around to here. That is theta. It's a really, really large angle. Cool. The terminal ray of the angle intersects the circle at point P. So here's point P. I don't have a coordinate point for P yet, but I can figure it out shortly. Because we want to find the following values. We want to know the sine, cosine, and tangent of that large angle theta. Based on my definitions, the only things I need to know here is x, y, and r for point P. So that means we need to know what the coordinate point of P is. How can we figure out what the coordinate point of P is? This is going to be your best help right here. If that point is 3, 4, and P looks like it's directly underneath it, what's the x value of P? 3. But since we have moved it down into quadrant 4, what do you think the y value of P is going to be? -4. That makes sense because in quadrant 1, coordinate points are always positive, positive. In quadrant 3, they're positive, negative. That's quadrant 4, positive, negative. Okay, fabulous. At this point, I have an x value, I have a y value, I have a radius length. I can tell you all three trig functions for point P. Sine is defined to be y over r. What's the y value here? -4. What's the radius length? 5. So sine of theta is -4 over 5. Again, I took this y value here and the radius length of 5. Which means for cosine, what is the cosine of this large angle theta? Look at the formula for cosine. It's what over what? So for this coordinate point, it's going to be what over what? 3 over 5. Fabulous. For tangent, the definition of tangent is what over what? Y over x. So for this coordinate point, what is the tangent of theta? -4 over 3. As long as you know the coordinate point of P, x comma y, and the radius length, you know all three trig functions. It's as if you knew all three sides of a triangle. You knew the opposite, the adjacent, and the hypotenuse. Same vibe. Just because I think it will be helpful for later, and these are your notes, we're also going to highlight the tiny triangle that is created in what's called the reference angle. We'll get into that later. But I want you to highlight the vertical displacement, which is here in pink, the horizontal displacement of point P in blue, and your radius length in green. Those are the same numbers we used from the coordinate point in that color scheme. That is the x distance, horizontal distance, the y displacement, -4, and the radius length of 5. Now it looks like a cute little right triangle that you would have done all of the regular trig with last year or 2 years ago in geometry class. Comments, questions, concerns? So for the rest of the notes for today, and we're going to stay on this topic for 2 days. Next time we're going to really work with what's called the unit circle. But today we need to start understanding the types of angle measurements we're going to use in my class. So our second and third page today are all about measuring angles. In geometry class, you probably measured all of your angles in degrees. Yes? Protractors give you angle measurements in degrees. We do not use degrees in this class. We're going to measure all of our angles in a measurement of angles called radians. You might have done a little bit of this in geometry, but it probably wasn't clear yet. A radian measure of an angle in standard position is the ratio of the arc length. Arc length is like the pizza crust. The crust length, part of the circumference, yeah, to the radius of that same circle. So we have this formula right here for the angle in radians. It is the arc length divided by the radius. Okay, in the same way a degree is 1/360th of an entire circle, we also kind of want to know what's happening in an entire circle, but in radians instead of 360 degrees. So here's how we figure this out. The circumference of a circle is 2 pi r. That's the formula for circumference or perimeter of a circle. Therefore, what is the angle created by a complete revolution of the circle? So a theta of 1 revolution, the angle measurement here, the arc length would be the entire circumference, 2 pi r. That's the formula you've used since elementary school for circumference, all the way around a circle. Our arc length is the whole thing. But our formula says to divide this by what? The radius. What letter do we use for radius? R. What do you have on top and bottom right now that you can cross out? R's. So what's left? 2 pi. Just like the math fact that a circle has 360 degrees, an entire circle, 1 revolution, is 2 pi radians. That's also going to be on your formula quiz next time. How many radians are in a complete revolution of a circle? 2 pi. Okay? Now, this means that every time we go around a circle, we can share the terminal ray, they're called coterminal angles, by a different number of revolutions. So now we not only can just go around a circle once, we can loop around a circle many, many times and end up in the same terminal ray. Those are called coterminal angles. Some more definitions for you. Positive angles are angles that go in the counterclockwise direction. So if you noticed in the last 2 examples, we started the positive x-axis and went around counterclockwise. Negative angles go in the clockwise direction. So we can go both directions around a circle. One of them is a positive direction angularly, and one of them is a negative direction. Since we are using the coordinate plane to define angles, we will eventually be able to consider angles to have periodic behavior because they can go around a circle and then go around a circle again, repeating that period every 2 pi radians. The main idea for today, though, because like I said, next time we're going to get into the actual values for sine, cosine, and tangent, is that I need us to understand the important angles that I'm going to ask you lots of questions about for an entire circle. Okay. For each of the following, what we're going to do is sketch a picture of the angle described based on a unit circle. Label the multiples of each angle around 1 revolution of a circle. So here's what I want to do. If I want to take 2 pi radians and divide it by something so that I get pi over 2 as my angle, what do I have to divide 2 pi by so that it reduces down to pi over 2? 2 pi divided by what is pi over 2? 4 is correct. So what that means for us is that we want to take an entire circle and cut it into 4 pieces. This feels silly because you're like, there's a coordinate grid already doing that. I agree. If I cut this like this, 1, 2, 3, 4. Do you see how I have 4 pieces of this entire circle? One of those 4 pieces is pi over 2. So if I start my angle theta and go from the positive x-axis to that first pizza pie slice, that is your angle pi over 2. That's theta. So that means for me that this direction right here, what you would have called 90 degrees, a right angle, is pi over 2 radians. But what I want us to do also is know the multiples of pi over 2 all the way around the unit circle. So what we're going to do is we're going to label these in an annoying way, and I promise I'll simplify it later. This first stop right here is 0 pi over 2. This is 1 pi over 2. What would this be? 2 pi over 2. But if you write down 2 pi over 2, what does that reduce to?
Just pi.
Just pi. The same way 0 pi over 2 is 0. Okay, so 0 pi over 2, 1 pi over 2, 2 pi over 2. What's this one? So 0, 1, 2, 3 pi over 2. And if we finish it all the way up, what's this one? Yes, 4 pi over 2, which, yes, what does that reduce to? These are called the quadrantial angles. So they're the angles on like 90, 180, 270, 360. But these are the values I need you to know in radians. We need to recognize these angle measurements and know where we're looking in a circle for these particular angles. So this is 0, pi over 2, 2 pi over 2, which is pi, 3 pi over 2, 4 pi over 2, which is 2 pi. Yes?
Yes.
Fabulous. Let's do another type of angle. This time we're going to look at the angles that are pi over 4 in the counterclockwise direction. So we're going in a positive direction. Same way we started this last one. If I had 2 pi, a first full circle, what do I have to divide it by so that that fraction reduces to pi over 4? Two pi divided by what? 8. So that means what I need to do is split this entire circle into 8 pieces. We're going to do this in a organized fashion, and I'm going to do this in pink. In pink, we're going to split it in 4 first, which we've already done. And then I'm going to take those 4 sections and I'm going to split those in half both ways so that I end up with 8 pizza pie slices all the way around my circle. Does that make sense? So that means for us that this first angle right here, the first pizza pie slice, represents the distance angularly, or the angular, yeah, whatever, pi over 4. Let's look at the multiples all the way around this unit circle. And I'm going to start back down at 0. So this is 0 pi over 4, which, yes, is 0. Then you have 1 pi over 4. The next pink line would be what? Wait, so if this is 0, this is 1, what's the next one? 2 pi over 4. Ooh, but can we reduce 2 pi over 4? Yeah, pi over 2. Oh, wait, pi over 2? Isn't that what I already had up there? Nice. Good job. Okay, let's keep going. So the next pink line, what is that one? 3 pi over 4s. What's the next one? Pi, because it's 4 pi over 4. The 4's cancel. We just get pi. What's the next one? So we have 0, 1, 2, 3, 4. Do we see how this pattern works? We have 5 pi over 4. Then we'll have 6 pi over 4. What is 6 pi over 4 reduced to? 3 pi over 2. Oh, look, that's exactly what we had written down here. What's the next one? Seven pi over 4. And then if we finish that full circle, it's 8 pi over 4. Y'all heard that? Okay, so here's the deal, is we have all of these multiples of this angle pi over 4 all the way around our unit circle. If you were wanting to know what this was in degrees, this is 45 degrees. So we'd have 45, 90, 45 plus 45 makes 90, all the way around this unit circle, but now we're measuring this in radians instead of degrees. So far we have seen our 90 degree multiples, our 45 degree multiples, which is pi over 2 and pi over 4. We have 2 more to do this with. We're going to do this with pi over 3 in the counterclockwise or positive direction. So same vibe as before. If I have an entire circle 2 pi, what do I have to divide it by so that it reduces down to pi over 3? 6. So that means I somehow need to split this circle into 6 equal parts. Follow along with me. We're first going to cut it in half this direction. So we're going to take our flat line and cut it in half. We're going to ignore the positive the y-axis because we don't want to split it there. But what we can do is we can split the top and the bottom themselves into 3 equal pieces, which is now 6 all the way around my circle. Do we see how we split this into 6 equal pizza pie slices? 2 pi divided by 6. So one of these pizza pie slices is that angle theta, pi over 3. If we start going around the circle with the multiples of pi over 3, we can do this. So we'd start with 0 pi over 3, which is 0. We have 1 pi over 3. What would be the next green line? 2 pi over 3. What about the next green line? 3 pi over 3, which becomes pi. Then we have our 4 pi over 3, 5 pi over 3, and 6 pi over 3, which reduces to 2 pi. So we have these values and multiples of pi over 3 all around our unit circle. Pi over 3 is like 60 degrees. So we have 60, 120, 180, on and on and on around our unit circle. But now we're measuring in radians. We've got one more. Our smallest angle, pi over 6. What would I need to divide 2 pi by to get it to reduce to pi over 6? Yikes, we need to split this pizza pie into 12 equal slices. We're going to do this again in a very systematic way. But let's first start by cutting it into 4. Then each of those 4, we need to cut into 3 pieces. So I'm going to have very small pieces all the way around our circle, cutting each of the quadrants into 3 pieces. So that you end up with something like this. Okay, those weren't perfectly equal, but you get the idea. They should all be equal, all 12 pizza pie slices all the way around the circle, because we divided it into 12. 6 on top, 6 on bottom. Just one of those pizza pie slices is our first angle, pi over 6. We do need to go all the way around this circle with the measurements. Let's start at the beginning. We know the first one is 0 pi over 6, which is 0. Then we have 1 pi over 6. What would be next? What is 2 pi over 6 reduced to? 1 pi over 3, which looks in the same position as that first green angle. That's pretty good. Okay. Our next blue spot would be 3 pi over 6. 3 pi over 6 reduces to 1/2 pi, or pi over 2. 90 degrees, pi over 2. We then would have 4 pi over 6, which reduces to 2 pi over 3. Then our 5 pi over 6. Then our 6 pi over 6, which reduces to pi. 7 pi over 6. 8 pi over 6, which reduces to 4 pi over 3. 9 pi over 6, which reduces to 3 pi over 2. 10 pi over 6, which reduces to 5 pi over 3. And 11 pi over 6. Before we make it all the way back to 12 pi over 6, which is 2 pi. Oh my gosh, that's a lot of values all the way around the circle. Specific values in these circles that I actually want us to go back and highlight. What I want us to do is highlight all of the values that didn't get reduced, meaning I'm going to start with pi over 2 and 3 pi over 2 for my y-axis, my 90 and my 270. In the pink, I'm going to highlight pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, because the rest of them reduced to another number. In the green, I'm going to highlight pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, because the rest of them reduced to another number. In the blue one, I only have to highlight 4. It's the pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. The reason I'm having you highlight these is because these are the angles I need you to recognize immediately. The rest of them are all multiples of a smaller angle. So I don't need to memorize those because they're already highlighted technically on another graph. But we need to recognize these angle measurements around a circle. I'm telling you right now, your entry ticket to the classroom next time, if you come to class on time, is a picture of an angle that's going to ask you, what measurement is this angle? And you're going to have to tell me pi over 6, 5 pi over 6, something like that. So we're going to recognize where these angles are in a circular motion. But to make this a little bit easier for your eyes and for your brain, let's put them all on one circle so you recognize the values I actually want. So we're going to clean this up with just the values that I need you to know. None of the multiples, nothing crazy. Let's start with our quadrantial angles. So we have 0. We would have pi over 2. We would have pi, and I can't reach that one. And then we would have 3 pi over 2, all the way ending back at 2 pi. Those are our quadrantial angles that I need you to recognize. Yes? If we fill in just the pink ones that I told you to highlight, the middle of the quadrant 1 would be pi over 4. Might be helpful to highlight that one in pink if that helps you. Pi over 4. The next pink only angle was the middle of quadrant 2. That was the number 3 pi over 4, the angle. The next pink one was the middle of quadrant 3, which was 5 pi over 4. And then we have the middle of quadrant 4, which is 7 pi over 4. We'll go green after this since that's the order we did this. The first green angle is pi over 3, which is bigger than 45 degrees. It's bigger than pi over 4 because it has a smaller denominator, which means this first green angle is our pi over 3. The next green angle is the very next line that's not quadrantial. So this one is 2 pi over 3, sorry. just to make this easy, here's what I want you to notice. Do you see how these green ones are like the insides? Like not the quadrantial, but they're next closest? Which means down here, they're also going to be the next closest. So my next green lines are this one and this one, which would be our 4 pi over 3 and 5 pi over 3, not 6, 3. Which means all that's left is those nice, neat multiples of pi over 6. So I have the first pi over 6. That's the wrong color. Then we have this line as pi over 6. That's 5 pi over 6. This is 7 pi over 6. And this is 11 pi over 6. That is a crooked line. Let me fix that. So these angles that we've now put around an entire revolution of a circle, I need us to know where they are and recognize them. Okay, here are some tricks of the trade to recognize them. Quadrant 1 is very easy. The denominators get smaller. 6, 4, 3, 2. Check. After that, you're going to look at what's called the reference angle. So compared to pi, if we go up into quadrant 2, that's going to be less than this number by 1. So 5 over 6, 3 over 4, 2 over 3. Underneath pi, it's 1 more than the number. 7 over 6, 5 over 4, 4 over 3, 3 over 2. In this quadrant, if you think about finishing a full circle, it should be 1 less than double the denominator. So double the denominator is 12, 1 less is 11. Double is 8, 1 less is 7. Double is 6, 1 less is 5. Double is 4, 1 less is 3. So those are quick ways to kind of recognize where in the circle you are. I like comparing it to these flat angles here, 0 and pi and 2 pi. Okay, looking forward to next class, because next class we're going to really work on the values of sine, cosine, and tangent around a unit circle and spend the whole day working on that. But we get to change our definitions of sine, cosine, and tangent when we're working on a unit circle, which will help us next class. These are not the definitions I want you to have for my formula quiz. I do want you to have the ones from the front page, but this is important. When the radius is 1, that's when we're working with what's called a unit circle. So we have a radius of 1, or we have a hypotenuse of 1. Whatever the value is of that terminal ray, it's going to be 1 because we're on a unit circle. Which means our coordinate points for P now tell us a bit more information. Because our normal definition for sine was y divided by r, what's y divided by 1? It's just y. So on a unit circle, our sine and cosine definitions get simplified because they're just y divided by 1 or x divided by 1. So it just looks like we're really looking for that horizontal or vertical displacement without needing the radius, because the radius is 1, we're dividing by 1, doesn't matter. Please note that the definitions for tangent did not change because they're not defined by the radius at all. So it's still y over x or sine over cosine. Vertical displacement divided by horizontal displacement. Next class, we're going to build an entire unit circle with the values all the way around it so that we actually know what the x and y coordinates for each of the coordinate points on a unit circle, point P, for each of the angle measurements that we just had. But that's a lot. We've already got a lot in our brains. So we're going to stop this for today and pick this up next time with the actual unit circle.